Good evening, everybody. I am Deeptosru, the coordinator of PICS Today webinar series. Welcome you all, and a very good morning to Dr. Ajay Jacob. Today, we are very fortunate to have him from Southern California's Information Science Institute. He is the director of the institute. We are going to have a very interesting topic from him, which is like quantum chip interposer packaging. Before having this exciting talk, I would like to request Professor Vijay Krishna Das to introduce our honorable speaker. And also, I like to request Professor Anil Prabhakar to handle our Q&A session at the end of the talk. Over to Professor Das.
Yeah, thank you, Diptasri. Happy New Year to you all, and welcome for this webinar series. It is indeed, we are proud to introduce Dr. Ajay Jacob, who is a director at the University of Southern California Information Science Institute, and has been leading application-specific intelligent computing lab since October 2019. He brings about 16 years of experience from Intel Corporation and Global Foundries to ISI. And Ajay has more than 250 worldwide issued patents, out of which 197 US patents already published, and many of them are in the US PTO office for approval. And he also published 3 book chapters and more than 75 journal papers and conference papers, internationally reputed conference papers, and contributed papers in many areas, a wide area of applications, scaled and differentiating technologies. And specifically at GF, that means Global Foundry, Ajay was awarded the title of Master Inventor between 2017 and 2020. In 2013 and 2016, he received Mehboob Khan Outstanding Industrial Innovation Award from Semiconductor Research Corporation. And currently, he is serving the chair for a Silicon Photonics session for 2022 IEEE conference, IEEE Electronic Components and Technology Conference. And also in 2022, he is also chairing session for International Conference on Frontiers of Characterization and Metrology of Nanoelectronics. So he is bearing a huge experience, as you can see. So we'll be looking forward for his exciting talk on quantum chip interposer packaging, which is, packaging is a very important aspect of IC integrated circuit, either both in electronics domain as well as photonics domain. Photonics domain, the design rule is still being developed. So it would be good to listen the exciting talk, how this is progressing so far. Over to you, Dr. Jacob.
Thank you so much, Professor Das, for this introduction. Let me share the slides. I hope you can hear me well.
Yes, it's coming.
It's coming. Okay. So once again, thank you, Professor Das, and also your team for inviting me to give this talk. It's a pleasure to be here to give this talk on quantum chip interposer packaging. So unlike, unlike regular packaging, here I would be discussing about novel packaging methods to integrate quantum computing components. So let me acknowledge my contributors to this presentation, and some of these names should be very familiar to you all. Dr. Ramesh and Dr. Sujit, both graduated from IIT Madras under Dr. Das's supervision. So I should also say most of this work in this presentation is done by Dr. Ramesh when he was a postdoc in the AC group. So let me take a screen pointer. Okay. So before I get into the packaging, let me try to quickly introduce, give a brief on quantum computing. So, the idea of quantum computing is not new. It is at least 40 years old. So if I remember my journal readings correctly, it was first suggested by Yuri Manin. You might already know him. He now works in Max Planck Institute for Mathematics in Bonn. And less than an year, or probably in a year, Professor Richard Feynman from Caltech independently proposed quantum computing. And it became more more popular after all the algorithms started being developed. Quantum computing, the hardware alone did not survive, or the theory alone did not work, but algorithms had to be developed to support the quantum computing paradigms. So the question is, why do we need quantum computing? So to answer this question, let's quickly compare classical and quantum computers. A classical computer, as you know, has binary states, which is 2 states. So this essentially means that transistors can be switched on and off function, provides you with the 0 and 1 states. This means you could have 2 to the power of n possible states in a classical computer. Now, in a quantum computer, so we replace the transistors with another term called qubits, or quantum states. So quantum states can also be binary. However, if we invoke the quantum mechanics, and if we invoke the spin of an electron, the angular momentum of the electron should be considered. And when you consider the angular momentum of an electron, there can be multiple states. For example, there can be 2 upspins, there can be 2 downspins, there can be an upspin and a downspin, and a downspin and an upspin as different. So essentially, there can be different combinational states one can actually build from the angular momentum of the spin of an electron. This essentially means if we take the same 2 to the power of n principle, the quantum computing will have 2 to the power of n quantum states, and n being the number of qubits in the system. So in nutshell, if we have to popularize quantum mechanics, the qubit technology is what is very important, and number of qubits, the scaling of the qubits, is what we are all, I think almost all the researchers are after. And this presentation will try to introduce you to a method of scaling qubits. When we talk about qubits, I mean, it is the quality of the qubits that is very important. So we call in quantum chip interposer packaging, or QIP, we call it in short. And this is nothing but heterogeneous integration on an interposer. So let me now get to okay. So let me now get into the overview. I will discuss various quantum technology hardware platforms, the trends, challenges in scaling the qubits, how packaging is done in quantum systems, and I will then introduce the concept of quantum chip interposer packaging technology, followed by a deep dive into how we can fabricate a QIP. I will then discuss distributed quantum systems using QIP, followed by a quick summary. So let me begin the discussion introducing different quantum technologies that are available in the research market. Each has its advantage, it has its own disadvantages, and this is related to coherence, fidelity, ultimate scaling that you can have. I mean, how big a system can be built. So among these, the most popular ones, that I'm trying to show here on the screen, the superconducting systems there are pros and cons for each of these. I mean, and superconducting photonic ion trap, I would say, are the most competing today. Ion trap and the semiconducting are the most competing today. While you have the topological and also the PB centers, the nitrogen vacancy centers in the diamond, which is more in a researchy phase. So let me discuss a bit more in detail on the superconducting qubits. So the primary advantage of the superconducting computer is that it fits well with the current microelectronics process technology. So the core circuits, that we call the qubits, it can be charged qubits, it can be flex qubits, or it can be phase qubits. They are perfectly compatible with the current microelectronics processing technology. You should note that they are built of Josephson junctions. And if you have, let's say, a physics background, you might have learned about Josephson junction in your undergraduate lectures. It's relatively easier to fabricate a Josephson junction. It's nothing but a capacitor. As an example for the capacitor, I can say that alumina sandwiched between aluminum electrodes. I mean, you can consider as a simple Josephson junction at the cryogenic temperatures, though. So the wires connecting them and the charge in the capacitors, these are in superposition state compared to a traditional capacitor. And and as you understand, the Josephson junction, as I mentioned, I mean, they can be fabricated with microelectronics friendly materials, which essentially means that you may be able to fabricate this in a foundry, the superconducting junctions or a superconducting circuit. So the message is that the superconducting quantum technology, or the qubit technology, it is microelectronics friendly, and we can easily scale them. And scaling means we can add more number of Josephson junctions, or you can scale the number of Josephson junctions, which essentially means that you can have more qubits in the system. So the more qubits that you have, you can compensate for the error, or one can create a fault-tolerant computer out of the superconducting junctions. And for a superconducting system, the error happens because of the decoherence inside the qubit states. So it's getting. Okay. So the error in the superconducting system happens because of the decoherence. And this is one of the major disadvantage of a superconducting qubit system. And decoherence is especially fast when there is thermal fluctuations. And if you look into the other major contender, which is the photonic system, we talk about the squeezed light. It is probably difficult to generate squeezed light, but the history of squeezed light is not new. It essentially, it comes from the quantum theory. I mean, this is essentially associated with the amplitude and phase of any state of the light. And if this quantum uncertainty is not distributed equally between the amplitude and the phase of the light, the state is said to be squeezed. And the more the states that you have more number of the more number of photons that you have inside it. And more number of photons, at the end of the day, you have more number of discrete states that you can actually generate. And the way in which you generate the squeezed light is by having several optical paths. You can have corresponding beam splitters, and you can have the photon counters. And when squeezed light meets inside a beam splitter, what happens is they mix together due to the interference. And as a result, if the states come out completely scrambled, so the number of photons can be counted using a highly sensitive detector. And I mean, from a photonic standpoint, I mean, it is agnostic to the temperature. The light is agnostic to the temperature. However, it's not that easy to count the number of states. the detectors requires to be cooled down to the cryogenic temperatures, and photonic system was not that popular until until an appropriate algorithm was developed to filter out the squeeze light, or to filter out the qubits from the photons. So essentially, I mean, a set of squeeze light goes through several beam splitters, gets scrambled. You have a powerful detector that will now count the number of photon states, and using an appropriate quantum algorithm, one should be able to do the computation. However, this is not, it's not easy. It's easier said than done on a chip. So in order to create a larger system, it's actually difficult. So the other popular contender is the ion trap. And what happens is when a light is shown to an atom that has missing electrons, the qubits are generated. And the advantage is that you can actually control the qubits using laser, using a laser. However, you require to cool the technology to a few Kelvin temperatures. The other advantage, I mean, just as in photons, the other advantage is that it has longer coherence time because it is also emitting type of photonic qubits, but in a different wavelength regime, something around 1100. It also has better interactions with its neighbors, but the disadvantage is that in order to create several defect states inside the material is not that easy. And also the reaction, is also pretty slow in an ion trap qubit technology. While in the semiconductor technology, so it's microelectronics friendly. You can build the qubits based on either quantum dots, the single artificial atoms, or single spins using quantum gates. One can actually create qubit states. However, the challenge is in value degeneracy and also controlling the qubits inside the channel. And we have several major proponents for each of these technologies. For example, superconducting coming from IBM or Google or Rigetti, or the photonic coming from PsiQuantum and Xanadu, and the ion trap coming from Honeywell and IonQ. Each has their own proposition based on the advantages and the disadvantages one can anticipate coming out of this quantum technology. And in this, what we want to do here is to take the best out of this technology into a packaging format such that we can get quality qubits scaled for computing. So now let me talk about qubit roadmap. I mean, so what is important is the number of qubits. And if we talk about the qubit roadmap, we have all these proponents discussing about the number of qubits that can be generated. For example, IBM talks about superconducting qubits, and they have met their milestone for the year 2021 by bringing in or by having more than 100 qubits, and they anticipate to have more than 1,000 qubits by the year 2022. And by the year 2023, they believe they can have a system that can do a certain set of they call it quantum advantage. That's what they want to achieve in 2023. Now you can define what is quantum advantage, and I think it is to measure. It is a measure of the quality, speed, and scale of the qubit technology. And what is important, I mean, if you look at the other technologies, for example, the ion trap and the photonics, they are still poor in obtaining large number of qubits, even though they discuss promising outlook for scaling the qubits. What is important is you need millions of qubits, millions of quality qubits that are needed for better fault tolerance and error correction. So because decoherence is very popular in this qubit technology, you can easily dephase the qubits, and therefore you need more number of qubits to to filter out the quality qubits that does computation. One of the challenge is in having more number of qubits or in scaling the qubits with the current technology is that they are bulky systems and they are noisy systems. And you require to have, let's say, the superconducting qubits, you require to have microwave controller electronics, and also several coaxial cables and several other materials. And this is, I mean, if you look at the D-Wave quantum computer is placed in Information Sciences Institute, and it occupies the whole room. One single quantum computer occupies the whole room. So they are bulky systems, and what we have to figure out is how to make it smaller, how to bring the form factor of the whole system smaller. It's also important to address the heat management when scaling the qubits. It's also important to figure out having a reliable readout. And the control electronics, for example, that controls some of these superconducting circuits, they are still classical. They generate a lot of heat, and they are not closer to the qubits, which adds to the delay in the system. So as I mentioned earlier, photonic systems, though they are dependent on they're independent of the temperatures, the detector performance definitely requires cryogenic characteristics. It only performs well at cryogenic temperatures, and maybe one can actually build a room temperature photonic detector. But overall, from a photon, if we discuss about the photonic technology, the cryogenic performance of the optical system is not very well understood, is what I can what I understand. And then in order to create such a heavy system, it is the cost. It's the high. We have to also think about high volume manufacturing of these qubit scaling. So essentially, we need a balance between coherence, the connectivity, the control, and also the cost to make it very popular. Now, if we discuss about the qubit scaling, that the features of a qubit interconnect, we have to think about having low noise and low loss, which essentially means that it has to preserve the qubit coherency and reduce the crosstalk. It has to be scalable. There should be more number of qubits. It has to minimize the footprint in the quantum ambient. And it has to be also compatible with other quantum technologies. For example, the superconducting quantum technology should be compatible with the photonics quantum technology, or the quantum sensors that you built for one of the technologies should be able to be used for other technologies as well. And it should also be useful for the quantum communication network. And when we think about, one of the major challenge, it's not just in the quantum computing, but also in the classical computing, we have the interconnects, or the transport of the data as in a classical interconnect, as in a two-way country road. This is the traffic in a city that you can compare. While ideally, what you want is a divided highway system, as in a quantum interconnect, which essentially means that you have one set of spin polarized electrons travels only in one direction, and the other set of spin polarized electrons travels in the other direction, and they don't meet each other, or they don't just scatter each other, or they don't dephase by going through the classical country road through scattering or through other means. So what is important is we need to replace the conventional on-chip bidirectional conventional classical interconnect with a bidirectional novel interconnect, and we need to have novel materials to do that. We should also be able to introduce optical interconnects if possible, and the devices associated with the optical interconnects. And we should be able to package all of this together for a reliable quantum system. So essentially, a quantum optoelectronics interposer packaging that can address the address almost all the interconnect challenges, such as, so when we talk about the bidirectional interconnects, we should think about chiral interconnects. We should also think about electro-optic transducers for scaling. We should think about the backside optical coupling for the input-output. By taking all the good things from superconducting electronics, photonics, we should be able to create a system. And that's what is the Qubit, the QUIP technology that I'm going to introduce. So before that, let me quickly talk about the current packaging technologies. I mean, there are researchers working on packaging of the quantum systems. They package the single quantum system, such as, let's say, superconducting quantum systems are packaged both at Yale as well as in the MIT Lincoln labs. They do a 3D interposer level packaging technique. There are only a few publications out there, though. If you look into the photonics, if you look into the ion trap, I mean, it is a photonic interposer that they use to package the ion trap. Here, the difference is, interposer that has been introduced so far is either based on electrical only interconnect for the superconducting qubits, or it is an optical only interconnect for the ion traps. And for ion trap, the wavelength at which the qubits are generated, it's roughly in the 1000 nanometer range. So what we want to introduce here is we want to propose a heterogeneously integrated quantum chip packaging solution, that addresses multiple qubit systems, for example, qubit type 1 and qubit type 2 to seamlessly integrate together. We should have the directional interconnects to reduce the crosstalk. We should be able to have the electrical, optical, and also the electromagnetic on-chip interconnects. We should be able to have the integrated microwave photons to optical photon frequency converters. I mean, in a quantum chip interposer, we should also be able to convert from one frequency regime to the other frequency regime easily. And if we can convert this into an optical waveguide, the advantage that we are talking about in this optoelectronics interconnect is, the superconducting Josephson junction-based qubits, they have high decoherence. The photonic systems, as I mentioned earlier, they have larger coherence. I mean, they have long lifetime, which essentially means that if we can convert from the microwave regime of the superconducting electrons into the optical regime of the photons, I mean, the communication regime, then we could transport the qubits between the chips or between the dewars, or from one place to the other through optical fibers. So here is a schematic of a quantum chip interposer. So in this, we have multi-level interconnects here. Multiple chips are packaged in this schematic. There is directional chiral interconnects. I mean, you can think about the chiral interconnects over here. The chiral interconnects could transport both electrons as well as it could transport microwaves as well as photons. It should be able to package different quantum technologies: the superconducting technology, ion trap technology, the photonic qubits technology, all in one chip. The microwave to the optical frequency converter, that happens through a transducer. And if it has to be integrated onto a chip, I mean, there are several types of transducers, but if you have to integrate onto a chip, you need to reduce the form factor. And electro-optic transducers seems to have extremely small form factor that can be easily integrated into the into a chip. And also that we need to have directional microwave interconnects, circulators on this chip. The need for microwave interconnect is that directional interconnect. I mean, if you can build it of the topological chiral materials, the advantage is that they can be 1,000 times smaller than the conventional circulators. I mean, you probably know if this. So with chiral interconnect systems, one can actually build extremely small circulators that can be integrated onto the chip. I mean, with all these components, one could be able to create a distributed quantum system on the package itself. So this is the high-level overview, very high-level overview of how a quantum chip interposer packaging solution should be. However, a realistic chip should be much simpler than what I discussed in the previous slide. So in this particular system, you have very few features. You have the superconducting circuit. The superconducting circuit is independently fabricated, separately fabricated, and then they are flip chipped or bonded onto the interposer. You have the directional interconnects. I mean, these are using chiral circulators. And you have this on-chip 2D microwave circuits. You could assume these microwave circuits to be built of a chiral interconnect, which is bidirectional. And then you could have the quantum transducer, which converts the microwave photons that is generated from the superconducting circuits into photonic circuits. So you have this independent optical component that is integrated onto the interposer. And then the information is carried out through the photonic waveguide, through an I/O input-output optical fiber. And in the interposer, we should also think about integrating electronics, for which we can assume having TSVs through silicon vias. And some of these through silicon vias could be electrical, and some of them could also be optical vias, depending upon what type of chip functionality you are anticipating to build. So essentially, by having this TSV, we can have a Qubit control circuit that is moving to the bottom of the module. Another advantage of them moving to the bottom of the module is that you can independently control the thermal characteristics of the electronics out there. Instead of having a huge system where the electronics is way far up in the dewar, here you can integrate them onto the interposer, into another chip that is actually connected to the interposer. And then the thermal characteristics could also be independently controlled. So let me get into more details on it. For example, the choice of the materials. The interposer technology can be built of intrinsic silicon, microelectronics friendly. You can also think about various interconnects, which is built on niobium. It is the classical interconnect materials that are used today for the superconducting technologies: niobium nitride, tinitride. And we could also think about TSVs, which are built of superconducting materials, since the whole chip is going into a cryogenic temperatures. We could also have the indium bump bonds, just to interconnect between two different systems, especially the superconducting systems, with the control electronics. The optical system could have silicon waveguides, or silicon nitride waveguides, or aluminum nitride optical waveguides, or even the chiral waveguides. The topological chiral materials can be used for both optical as well as electrical interconnect. From a Qubit chip perspective, you could think of flip chip bonding and also the TSVs. They can be capacitively coupled to the TSV. This eliminates the need for bulky planar capacitors. The Qubit chip could also be inductively or capacitively coupled. The coupling between microwave feed lines, this can, here you can assume the gap of something about 5 to 10 micrometers, and it should be alignment tolerant within that distance for a heterogeneous integration. The chiral directional interconnects and circulators, this can be built of topological materials, and essentially the topological materials, what it does is it only allows one upspin, let's say upspin electron. It only allows one upspin. It only allows upspin electrons through in one direction, and maybe the downspin electrons in the other direction. So it's a non-reciprocal interconnect, and this can be 1,000 times smaller than conventional circulators. when integrated into the Qubit technology. So now the other most important component is the quantum transducer. And as I mentioned earlier, there are various types of transduction technologies available. You could think of optomechanical transducers or piezo-optomechanical transducers. We could think of magneto-optics transducers, or we could think of electro-optics transducers. They all have their advantage and disadvantage. The transduction technology can be used for frequency converting from the microwave to the communication wavelength regime, or it could also be, you could also think of frequency conversion from the ion trap, the light emitted out of the ion trap technology to the communication wavelength technology as well. You can think of different frequency converters there. Some of the advantage and disadvantage is that, when it comes to optomechanical or the piezo-optomechanical systems, it has low thermal stability and also the low scalability and tunability as well. While the magneto-optical system, they are actually big though. They have high thermal stability. However, because they are big, however, the scalability is poor, and also the tunability of the system is poor. And this is where the electro-optics advantage comes in. The G by 2 pi factor, the conversion rate, it's not conversion rate, should be 100 hertz to 10 kilohertz range, and the thermal stability is also high for an electro-optics transducer. It is also scalable and it's also tunable, and this is one of the reasons why we have chosen to work on electro-optic transducers. And what happens in an electro-optic transducer is that it is actually doing some frequency generation. So you pump in optical light, and then you add with the microwave light, and then you get an optical signal out. So it is important to figure out that, when in a superconducting junction, when the superconducting electrons convert into the microwave photons, we are assuming that one microwave Josephson junction can create one microwave photon qubit. And if we assume that the light that is the microwave photons that are transported carries one microwave photon, it would be a one-to-one transition into the communication conversion as well, communication regime conversion as well. So one microwave photon qubit should generate one communication wavelength photon qubit as well in the output. So we did some simulation. I mean, I have to thank Dr. Ramesh for all these simulations that he carried out. He designed this device. I mean, when I told him that, okay, we need to have some novelty brought into the transducer, as this is one of the most important component that is required to build the Qubit technology. He came up with this idea of having 2 disk resonators, which is embedded inside the microwave cavity. And this is for the first time, I believe, someone has proposed a double disk resonator inside a microwave cavity for quantum frequency conversion. So this particular chip, I mean, it is built on sapphire. Aluminum nitride is actually deposited onto it using disk, and you fabricate disk resonators. You have the top cladding layers with microwave top cladding layers, as well as the microwave capacitors on top of that. The aluminum nitride waveguide carries the photons in and out of the disk resonator. And as you see here, when you have this coupled disks, you can actually create. I mean, this is essentially the Stark effect. I mean, AT Stark effect is what happens here. It's essentially shifting and splitting the spectral lines of atoms and molecules, in the presence of an external electric field. So otherwise, AC Stark effect, this was proposed a long time ago by Ortler and Towns. Essentially, this is a linear AC Stark effect that happens in this two-level binary system, two-level system, which is strongly driven at resonance. I mean, what is important here is, I mean, you need to have resonance, and you can also measure using weak probing technologies, weak probing techniques. And these are some simulation results. essentially it shows that you can actually have an internal efficiency of roughly about 11% and an external efficiency of roughly about 3% at this roughly about 1 milliwatt input power. So what you see here is that you can do the, what you see here is, this is a scaled device. Compared to existing literature out there, which has much bigger footprint. Let's say the existing literature out there is either single ring resonators or maybe coupled ring resonators have also been proposed. Their footprint is very high, something about 500 square micrometers. While we are talking about here in the less than or roughly about 100 micrometer regime is where we have parked this quantum transducer or the quantum frequency converter. So that's the advantage. The form factor of the device is one of the major advantages here. And also the frequency conversion, this efficiency is comparable or better than what is out there in the literature. So another very important component for a transducer technology, for an interposer technology, is to have the input-output, the couplers, input-output couplers, and the fiber attach. Today normally the fiber attach is done using V grooves. You actually dig a trench, V groove trench, on the side of your chip, and then you connect the fiber onto the V groove, and then through metamaterial systems or maybe a tapered waveguide, you can focus the light inside the fiber. Here the fibers are very huge, and this waveguide is of the order of, the tapered region could be of the order of 100 nanometers, while the fiber is of the order of 700 micrometers. It could be of the order of that. It could be that big. You could also think of something of the order of 100 micrometers. They could be small as well. However, the challenge in the superconducting challenge in the cryogenic world is that this doesn't align very good. And this is when we thought that we could probably use a backside optical coupling. So we could probably etch trenches to the backside, and using metamaterial structures that acts as anti-reflection materials, you could think of aligning the optical fiber through the backside of the wafers. There is another advantage here. You could have multiple input-output fiber coupling to this chip. In an edge coupling, you have to edge trenches to the edges of the die, while in a backside optical coupling, you can have multiple V grooves, multiple V grooves etched to the backside of your die, and then you can have multiple fibers, probably more fibers than what you can actually build in a fiber-mounted V groove technique. And this is also, mechanically stable compared to an edge technique, and it should have a better cryogenic performance compared to an edge coupling technique in the cryogenic world. In the non-cryogenic world as well, I believe this should be useful for a PIC technology. So these are the primary components that goes into a quantum interposer packaging technique that interfaces multiple quantum qubit technologies and also multiple quantum technologies such as quantum memory devices, quantum sensors, or any other, and also the electronics that associated that requires to control some of these qubit technologies. So these are some of the components, and let me quickly get into another area. Which is, if we build all these components onto a chip, we should be able to anticipate creating a distributed quantum system using the QUB technology. For example, you can have a QUB system that is QUB1, which is based on one particular one particular qubit source, and you can have another qubit source in another place, for example, and they can be converted. You could have the up conversion or down conversion between them. These are the frequency converters, and you could connect these together between the chip or between chip that is separated each other in two different duos, or it could be between one place to another place. For example, from between California to, let's say, Chennai. So it could be one qubit technology, or it could be two different technologies. I mean, it depends upon the type of applications that one requires to type of quality qubits one requires to build and integrate. And one could think of creating a quantum network which is secure based on the hybrid, based on this heterogeneous integration scheme. So just to quickly summarize, QUIP, this is a heterogeneous quantum chip packaging scheme. We integrate directional interconnects. We have optical interface to this. We have microwave techniques that are added onto it, and we could also think of other qubit technologies added here. It's a chip level integration that bridges multiple quantum technology schemes. That's what I could talk about. That's what I could summarize on the QUIP technology. And we believe it can significantly improve the size, the speed, the power, and also the robustness of the quantum processes. And the chiral components, the novel chiral components, I mean, we require to it actually reduces the error rate. I mean, these chiral components could also be added on to other single qubit technology as well. But in this particular schematic, it provides bidirectional data transport without giving much room for error. Though there is thermal fluctuations one can actually anticipate built up on a chiral technology as well, the topological system as well. So having said this, I mean, I have to thank you all once again, and Happy New Year.
Yeah, nice, exciting talk. I think Anil, you can handle Q&A, and also I have in the panel Mr. Dinonath Sani and Deepa Venkatesh, Professor Deepa Venkatesh also, and for Q&As, Anil will be assisting Arnab, our CTO in charge. He will be assisting Anil in Q&A session. Yeah.
Thank you, Vijay. Let me also thank Ajay for this wonderful talk. I mean, I learned a lot about QUIP, which I knew under some other acronym, but Interposer technology was not something I was familiar with. There is
the QUIC technology, okay, which is interconnect technology.
We are in acronym worlds.
Acronym world, yes.
So there's a question here that asked by Shashank Kaushik, which is an interesting question. A lot of the reason we use cryogenic temperatures when we go to superconducting qubits is because of thermal noise and the interaction with the environment. And you're actually going down to point something Kelvin, few millikelvin, in order to do this. Now, a lot of the photonics technology actually uses thermo-optic phase shifters and so on to stabilize it. How are these two technologies going to coexist on the same chip or same platform? I mean, what are we going to do with the heat if one of them is heating and the other one requires to be kept cold? How are you going to achieve that?
So the beauty of a heterogeneous integration, interposer level integration, is that you can add thermal constraints to the system. That's the beauty. I mean, rather than an individual single technology where, let's say, I bring in superconducting electronics and separately bringing in other electronics, and if they're not packaged properly, then the heat is definitely going to create chaos. So there are two questions that I believe there in what you asked. One is about the photonics technologies. Photonics technologies definitely do not need the cryogenic millikelvin temperatures that is required for the superconductors. However, they do need cryogenic temperatures because the efficiency of their detectors depends on how low you can cool them. And I mean, as I mentioned earlier, you could probably think of discovering a new detector that works at room temperature. But today's technologies are all works at cryogenic temperatures. So the next question is, okay, do you really require the millikelvin cryogenic temperatures that is required for the superconducting techniques? The trouble with the photonic technology is that it is difficult to create qubits based on photonics. We talk about squeezed photons, but it is not that easy. It is not that easy to scale them. I mean, for example, if I go back to my roadmap, IBM is ahead of the game with more than 100 qubits that they have delivered. Their milestone was met this year. I mean, I think there was some article that I read from in December where IBM claims to have met their milestones for the year 2021. And they are probably going to meet their milestone of 1,000 qubits in the year 2022. While if you look at Xanadu as of 2021 has roughly about 46 qubits, and they propose to have their milestone for the year 2026 is 1 million qubits, and we have not heard much from PsiQuantum though. Which essentially means that it is difficult to create quality qubits based on photonic technology, and it is much easier, comparing various techniques, to create qubits based on superconducting techniques. And therefore, from what we have available today, we harvest the qubits based on the superconducting technology and then convert them into the photonic technology. And the disadvantage of superconducting technology is their decoherence. I mean, it actually phases out fast, especially when there is a thermal shift. What I know about is, in one of the, maybe IBM, I mean, they talk about having at least more than, or maybe close to 30 qubits, maybe close to 30 Josephson junction to create one single functional qubit. They could, I mean, because of the error correction that they need to that need to contain with the number of qubits that they have. So, but if you can convert the microwave photons that are generated through frequency conversion, if there is no loss there, then the photons have very large coherence length, and also it works at the communication wavelength regime. You can actually transport this across. The other question is, I mean, do we really understand the cryogenic performance of the photons? I mean, this is something that I want to mention. No, we don't really understand the millikelvin performance of the photons very well. I mean, maybe some people may know it. I mean, at least I should say the number of literature that I have found that studies the cryogenic temperatures, millikelvin temperatures of photons are very minimal.
Okay. Now that you have the slide here, I just wanted to point out that, IBM wanted us to move away from this idea of qubits and talk about quantum volumes. And actually, it turned out to be a bit of a strange thing for them, because IonQ quantum volume is hundreds or thousands better than IBM's quantum volume.
Yes.
So now IonQ, and actually Honeywell is missing in your slide. Honeywell, I think, has announced recently many more than IonQ already. I forget if it's 100 or 1,000.
I saw that article. I mean, yeah.
Their quantum volume is again, much better than what IBM.
I think I have it somewhere. I think I have it here, Honeywell.
Yeah. So it is interesting that even the definition or the metrics that people use in order to compare these things are very different. It's not just a qubit, because an IonQ qubit is much, much better in terms of fidelity than an IBM qubit. So the challenges there are, of course, different.
Yes.
There is another question here that I thought was interesting, which is about the topological chiral materials. There are two questions. One is whether it's CMOS compatible, And the other one is about are these interconnects highly directional when you use chiral materials? So do you have to worry about chirality when you're making interconnects to chiral materials?
Yeah. The first question is, are topological materials CMOS compatible? And yes, they are. I believe they are CMOS compatible. You can actually integrate them to the back end of line of the wafers. People have shown that you can create classical transistors based on molysulfide and various other types of materials, zinc selenide, all these materials on the CMOS platform. But ideally, it is better to avoid all these complex materials or all these complex elements that creates defects for the CMOS. You have to stack them to the back end of line region. And that's what we are trying to do here. Here we don't have much of the electronics out there in the interposer. Interposer is, so therefore, you can scale them on a chip. Now, one quick question is, okay, can you deposit these materials? Today we talk about various techniques like Scotch tape techniques and various other techniques to integrate these topological systems of 2D materials. There are research out there where you can actually try to deposit single monolayers or monolayers of these 2D materials on the silicon platform. However, is that a very mature technology? It is not that mature. There is still research that requires to happen from the materials standpoint itself. So that's the answer to the first question. And the second question is, I believe it is on how chiral these materials are, or how chiral. So ideally, the chirality is maintained. If you have, the only disadvantage is, they also succumb to thermal fluctuations. So if you maintain the temperature, the chirality is maintained, and the bidirectionality is also maintained.
Okay, so there is one more question here on what are the technological constraints on transferring qubits out of the cryogenic temperature while transferring from the transmitter station to the receiver? So this is always something, and maybe, I took down some numbers while you were talking. Even the double resonator device has an efficiency of about 11% or 3% externally. Something like that. When you have a single qubit and you're trying to make a measurement, every time you make the measurement, you're actually disturbing the system. So if you have an efficiency of 3%, then I don't know, maybe you have to make 100 measurements, more than 100 measurements to get a reliable reading. So what happens to the fidelity of the system when you do something like that?
Yeah, absolutely. So again, this is we are in the research world. So we ought to make many measurements to get one reliable data. Having said that, I think the first question. I think the first question was about how the photons are
technological constraints on transferring qubits out of the cryogenic chamber.
Correct. So one of the technological constraints is the heat, because when you are transferring this from the cryogenic world to the outside world, you have a thermal gradient there. So you got to make sure that within this thermal gradient, you are not destroying your qubit. For which, if you are trying to transfer this using a superconducting qubits, if you're just trying to take the qubits that are generated out of this microwave photon, so let's say the superconducting qubits, it's going to get destroyed faster. The decoherence is going to be very fast, while the decoherence is going to be slower when it comes in terms of the photons. So the thermal constraint is an important consideration. The second consideration is, how do you take the photons outside the cryogenic world? And there was a project out there. There was a big program out here as to figure out how to transfer data from the cryogenic world to the outside world using edge couplers. And I believe they have not produced very promising results, for the reason that these are mechanically unstable. Even at room temperature, edge couplers connecting the fibers, they are not mechanically very stable. There are lots of challenges out there. You already probably know about it. But you can imagine how unreliable it can be at the cryogenic world. And this is where what we thought is, hey, why can't we have backside optical coupling where you actually put your, where you actually flip it and then directionally keep your fiber inside the V groove and then take the fiber outside. You need to have a different couplers to be designed to take the photons outside the cryogenic world. For example, here you can think of a tapered waveguide, or you can think of a metamaterial based silicon waveguide. And here we are thinking of metamaterial structures, but with some that can actually help you with anti-reflection part, because these are some type of a grating structures that we have created with the metamaterials, and the grating structure is actually going to transfer the light. There could be other techniques also where you can actually transfer light from the chip to the fiber. One could also think about phase coupling to couple the phase of the material here to the phase of the material that you have down here that is deposited, and the phase coupling could also probably transfer the data from the chip to the outside world. But the primary two considerations, thermal and also the mechanical.
So maybe I'll ask Mr. Soni to comment on this, because he's quite familiar with what it takes to do this in an industrial scale.
It's still experimental.
Still experimental, right?
Absolutely, absolutely. I'm with Prof on that, and I know what he's saying. It takes a hell of a lot of work to get this done, and so far we've not done it in India yet. Of course, the direct coupling and through graded coupling and all that is fine, but this is something new even for us. This is something that we need to try it out. Yeah.
Okay. All right. Well, we are close to the end of the hour. Vijay, should we be...
Just one, I have one question to Ajay. So just when you say that coupling efficiency from microwave to optical is just 2% or something like that, is that because you are talking that one photon to one photon conversion, because of this energy of optical photons are much higher than the microwave photons, is that the constant or what technological constant? I would like to know.
I guess, is it a quantum efficiency problem, or is it, if you remove the effect of the quantum efficiency, is it still an inefficient device?
And how to improve, of course. Yeah. What is the constant?
Yeah. So two things. One is you need to have an efficient flow of microwave photons through your feed lines. The other is you need to have very good coupling between the microwave photons and the optical discs or the optical cavity. So the coupling efficiency of the microwave cavity to the optical cavity is very important here. And then the conversion happens within this optical cavity. And that is probably more straightforward. But the primary challenge, I guess, is the coupling efficiency between the microwave photons to the between the microwave cavity to the optical cavity. And the reason, so if you look into the literature, the efficiency for in the literature is much less than 11% for various other techniques, as various other electro-optical transducers, frequency converters, and we have obtained much higher, compared to 0.1, 0.2, 0.3% to roughly 3% here, and we believe it is because we have used a double disc resonator with a more optimal microwave cavity coupling. So that is what we believe. So again, so I just want to tell you some story. The idea of quantum conversion, the microwave photons to optical photons. This is not new. Way back in 2000, I've read literature starting from, at least from 2007, that comes from IBM, that talks about 1:1 conversion of the microwave photons, 1:1 conversion of the microwave to the microwave photons, and from the microwave photons to the optical photons. I mean, that's what they discuss, and it's a theoretical work. But it took almost, let's say, 2007 to 2000, almost 13 years, and still we are in this efficiency. And I believe this is not because there is a fundamental challenge, but it is an engineering challenge. And it is improving, is what I believe. The other techniques out there, which is the optomechanical or magnetooptics, I mean, they have much higher efficiency. However, the trouble with them is they are not small.
Yeah, the size goes up, yes.
Yeah, size. The size advantage, and therefore the power advantage as well.
True.
So one associated question. So when you say that this thermal gradient is one of the major problem for photon coherency you are losing, right? But I suppose that this thermal gradient, it will just, it may increase or decrease your latency, but how that will affect your coherency? If it is not at all scattering or something happening in the waveguide.
Oh, with respect to the photons, it is the decoherence or the error happens because of scattering.
Scattering, but that
Scattering.
is that due to the thermal gradient? That is what you mentioned.
So thermal gradient that I mentioned primarily for the superconducting electrons. You cannot directly take a superconducting electrons or even the microwave photons, I guess. I mean, they do have thermal coupling issues.
And another question, I just you just answered that Sasank's question, that thermal things. You just mentioned that this heterogeneous integration interposer that can solve the problem. But even if you do heterogeneous integration, your superconducting layer, the qubit layer, that has to be very, very low temperature. And you cannot maintain there at that level of temperature and immediately upper whenever you are just 3D integration you are doing for photonics, etc. That cannot be. I suppose that even though you do 3D integration, entire chip, packaged chip should go into the refrigerator, cryogenic chamber.
That is correct. So I think I mentioned this. So if you want to create quality qubits, the technique out there is superconducting. And if you go for superconducting qubits, then you have to go to cryogenic temperatures. However, you only create quality qubits at the cryogenic temperature with superconducting electronics. If you want to take those qubits outside, it is going to be, the decoherence is going to kick in fast. So therefore, you convert this into photons, where the occurrence length is much larger, much longer, much larger. And then you can take the photons outside. So you don't have a leeway out of the cryogenic world, though, unless you come up with a superconducting technique that works at room temperature or higher temperatures.
So you are not having any photonic circuit in the packaged structure. You only use the conversion and just transport. That is what you are using for optical networking. Yeah.
At least in a practical sense, that is what we are trying to do. However, in the long run, I believe one could also be able to have, the quantum sensors or, multiple photonics-based sensors or photonics-based memory. All these things could also be integrated onto the chip, and it can function at the cryogenic temperatures. It should ideally be possible if we ignore the cryogenic part of the temperature in our in the proposal.
Okay. Okay. Thank you.
You don't have a leeway out of the cryogenic world for the quantum.
There's no free lunch or dinner,
Yeah,
on
sure.
which part of the world you are in. Okay. Well, maybe I think, do any of the other panelists have any questions for our speaker?
Deepa left probably, yeah.
Yeah.
Well, if not, maybe I'll hand the mic back over to Deepashri. Thank you, Ajay, for the wonderful talk.
Thank you.
Really, lots to digest and think about.
Yeah, thank you, Dr. Ajay, for such a nice talk. And also, I thank you to Professor Anil for assisting this Q&A session nicely. And thank you all the participants and attendees for your active participation. And I want to see you all in our third webinar, which will be delivered by Dr. Rokens from Ghent University, Belgium. So have a nice evening.
Thank you very much. Yeah.
Thank you.
Thank you. Thank you all. Bye.
Thank
Bye.
you.
Thank you.
Okay.
Bye bye.
Pleasure.